sewing them into fabrics, using them in applications that, people haven't even thought of.
Which is
Yeah.
just where we are, because
Right.
we never ever would have thought about sewing them into fabrics for, to replace hook and loop. I mean, that's right, and it's very difficult to imagine, isn't it? The potentials until somebody comes up and says, "I've got a problem," and you could possibly fix it with a magnet,
Right.
with the right sort of magnet, and that's one of the key issues, isn't it? It's understanding and knowing precisely what type of magnet is required to do the job, and do it in a competitive way, economically competitive way. That's the other thing, because the materials vary from a few cents a pound, if you're some of the very basic ferrites, to $2,600–3,000 a pound. And if people don't understand, and why would they, the difference, then they're going to always say, "I want the strongest magnet." The strongest magnet may cost you that class of money, and you really don't want that if you're just producing a jacket, for example, that's got magnetic closures.
Right. And the other thing you got to consider is what are the actual properties that you're looking for? Are you looking for something that's going to withstand high temperatures? Are you looking for something, that's just going to be used at room temperature? Because that's a whole different type of magnet that you would be looking at potentially.
That's absolutely correct. And I think it comes down to, I'm not here to criticize education in this country or any country if it comes to that. But the plain fact of the matter is there's been no real formal education on magnetics certainly in the United States. Ever. That is one of the problems that we have today in designing products. We don't have a lot of magnetic engineers who are falling out of the universities. If you're studying ceramic engineering, you're studying electrical engineering, you're going to do a course on magnetics. But that's not good enough today. No. You've got to go way beyond that, particularly as we've gone into rare earths, which only really started in the 70s.
Yeah, and I mean, everybody likes to use the term rare earths, but everybody always the kind of the running joke is there's nothing rare about rare earths.
Nothing rare about them at all. The interesting thing is how they were developed, because they came about under the legislation of Richard Nixon, in that he reduced what's called the CAFE regulations, CAFE. CAFE regulations is the combined average fuel economy for a company. So it's a company's, let's take a company, Ford Motor Company, could be GM, it could be whoever, but the overall output of their vehicles, top to bottom, had to reach a certain average of fuel economy. So let's say that it was dropped down in those days to 22 miles per gallon. So as long as they didn't exceed that, they were doing fine. And the goals, of course, were reduced more and more. So how do you do that? Well, you do that by thinking about the weight of your vehicle. Mm-hmm. And how do you take weight out of a vehicle? In those days, the engine blocks were made of cast iron, for heaven's sake. Right. Heavy things. And they chose the starter motor on a pickup truck as the model to go for,
right,
and reduce the weight of that. Now, that was, again, a solid piece of cast iron.
Yeah, and it was like this big.
That's right, with even bigger than that. I mean, with ferrite magnets, which were that big.
Right.
Too. It's a hell of a weight to be moving around. So they chose that and developed, with that in mind, with that goal, a magnet that you could reduce in size. I mean, hugely. It came down to magnets that were something like, I think, maybe an eighth of the weight of the ferrite, but the size also. So you had more room under the hood, and you took the weight out. The CAFE regulations said 22 miles per gallon. You may have got another half or 1 mile per gallon. That was why it came about. And as a result of that, people realized the possibilities of miniaturization. You finish up with handheld tools, electric toothbrushes, these things. And when you think about in the early 70s, people were still winding their windows down with a crank.
Windshield wipers.
Windshield wipers. That was the first, actually. It was the first electric motor on a vehicle, funny enough. And now you've got trunk locks and hood locks and the sensors, and also if your gauges on your speedometers and so forth, tachometers, are all driven by magnets and rare earth magnets predominantly.
Right. Yeah, they're pretty ubiquitous in the world. Really, they're everywhere. I mean,
they are indeed.
Yeah,
they are indeed. And again, I come back to the point we were talking about earlier, that the expertise isn't freely available. So
yeah, I mean, they were actually developed. There were two competing technologies. There was one that was developed in Japan, and there was one that was developed in the U.S.
That's correct.
And the ones that were developed in the U.S. were they moved them out.
Yes, sadly. Great shame, and I think everybody would regret it today. But
Yes.
it was a division of General Motors who put all the work in and built a substantial plant in Indiana. But they sold it, and really, one can shake one's head. It's probably one of the great industrial gaffes that we could possibly make today, and it has in fact put all the main sources of neodymium iron boron, the principal rare earth magnet, in the hands of China, and you have no choice, but that's where the source is. But the use of neodymium and how to design it into a product is still done very much. We do that, and there are other companies like us, not many of us these days, but some of us who are able to design it and put it into the right level of magnetics and so forth, and then we have to obviously source it. And we have our source is second to none, I have to say. Obviously can't.
And long established.
Very long established. Very long established. I'm very pleased to say. Yeah.
Yes. So we've spent quite a bit of time talking about the rare earth magnets, and obviously there are multiple grades under there. But then there are also other magnets that are out there. There's just straight ferrite magnets, which you touched on as being kind of the original magnet. But then there's also alnico magnets, and there's
samarium cobalt.
Yes, samarium cobalt. Thank you.
Well, yes. When we at school, I mentioned education. I was talking about higher education, obviously, but when we were at school, and I was at school in England, but I'm sure the same thing happened here. When the subject comes up on magnets in physics or something like that, it's quite often you're given a horseshoe magnet and some iron filings or whatever, and you hold the horseshoe magnet over and you iron filings jump at it. And those absolutely were the first magnetic materials. It started with a material called lodestone, which has a natural magnetic effect, and into ferrite. There are several types of ferrite, and it not quite as complex as neodymium iron boron in the varieties, if you like, but it's certainly in the ferrite area, there's several different types. It's a very good material for sintering, to make a hard magnet through the sintering process. It can be injection molded, mixed compounded with normally a nylon. That produces a good magnet that is near net shape, of course. You can cast gears onto it, or mold gears onto it, and so forth. You can extrude it,
Okay.
And that is, of course, the heart of your refrigerator door.
Yeah.
And what is the seal? There's a bellows in which there is an extruded ferrite magnet. Shower doors the same way.
Yep.
So when there's quite a range there, and also I would point out that the way you magnetize ferrite magnets also makes a big difference to the strength of the magnet. Whether you magnetize it in the process of molding it, then demagnetize it to get it out of the mold, and then remagnetize it. That gives you quite a higher strength magnet. Or whether you just sinter it or mold it and then magnetize it afterwards. So that gives you a lower range. But again, there's a cost difference between the two, and
Sure.
it depends on the cost effectiveness of the end product and what
Right.
choice you need. Again, we don't, and I'm sure not many people in the magnet world would necessarily go out to say, you need this if you don't need this. I mean, you need to get the right magnetic strength that you require in the size. The others you're talking about, of course, have been around a long time. Alnico is an alloy of aluminum, or aluminium, as I would call it, nickel and cobalt. Used a lot in motors. Actually, it's one of the ones that has been used for many, many years in devices like seat adjuster motors.
Okay.
Now actually replaced quite often with rare earth because it's smaller.
Yep.
Alnico magnets are unfortunately not friendly to the environment and can be cast or sintered, but they're not particularly popular, and there's less and less of them. Samarium cobalt, however, has been around quite a long time. It resists heat. Heat can often take magnetic strength out of a magnet. But samarium cobalt's been used for a long time by the camera industry, for example, for small motors in cameras for the wind-end mechanism and so forth. Still around, still needed in some applications, particularly, again, where there's a high temperature, so you don't lose the magnets. So, it's a big field. It's a very big field.
Yeah, I think that, just in talking, I mean, I think, anybody that's listening to this can understand that there's a wide variety of choices out there for, whatever magnetic material you might need. And then, you need to partner with a company and group that actually understands those various options that you have, the properties of them, what product is going to work best in your application, rather than just going to a catalog and saying, oh, I'm just going to grab a rare earth magnet, and you really don't know what you're getting. Working with TyTek, you're going to get the knowledge that, comes with the experience of having worked in the industry for, a great number of years.
Well, Clint, you just touched on something that I think is very important, that a lot of people don't necessarily know, or certainly don't think about. And that is that the producers of neodymium iron boron materials produce them under a license, and that has been so since day one. There are, because of the demand, there are people that are producing or trying to produce neodymium iron boron magnets that are not produced with licensed material. And there's a tremendous amount of variability you can get with that.
Right.
You have to really be looking carefully. And when you talk about going to a catalog or online and you see, magnets and you just sort of choose one, you want to be sure that magnet, if you're making or needing 50,000 or 100,000 or 500,000, the first one is going to be the same as the 100th one, is the 1,000th and the 50,000th. And that's where people have had a lot of problems. And if they're working with a company like TyTek, they don't have to worry about that.
Right.
The material is licensed. And absolutely consistent and certified, and we produce the magnetic testing results to any customer that wants them with every batch if need be, just to be sure. They can rest assured on that. If you're not aware of that and you are doing the catalog route or whatever, you can be in quite a bit of danger that your product's not going to be consistent.